Hi everybody, my name is Logan Pulowski. I've come to speak to you today to solve how the internet works. We're going to look at how the internet works through total internal reflection. So in order to talk about the internet first, which works through a process of total internal reflection, we're going to talk about the reflection part first. So the first thing that we have to know is that light reflects. So here I've shown, I don't know how many of you have played pool before, but if you ever played pool, you know that when you hit the cue ball, or maybe you've played it on Game Pigeon, right? Some 8-ball. Optics is basically just 8-ball with light. That's how we're going to think of it, right? When you're playing pool, you shoot the cue ball in at a 30-degree angle, it's going to exit the same angle. Light does the exact same thing. The incoming ray is reflected at exactly the same angle that it was incident at. So that's the one property of light, right? Reflection. Light also refracts. Say a surface isn't completely reflective, like this surface. You've probably seen that, the light can go through things like glass. But as the light goes through, it changes its angle at which it's traveling, and then it exits parallel to the incoming ray. So if we took this array, you can see the light has just been displaced. Now it's kind of, it's maybe not, entirely intuitive when you look at that. And I kind of have a diagram up there showing what's happening, right? You have a partially reflective surface maybe. Light comes in, and some of it's reflected at the exact same angle, like we just talked about with the cue ball. But some of it's refracted, and that angle is not the same. So the question is, what's happening there? The same phenomena happens when you look at something in a lake, and it looks different, it looks distorted. You reach in to touch it, and you try to grab it, and you're not there yet. And that's exactly what's happening with this pencil, right? If I reach my hand in, I'm going to try to grab that, but really it's down there. And so that's what's happening with refraction. And what explains this is the lifeguard scenario. If I were to ask you, if you were a lifeguard and there's someone out there, there might be a shark right there. I'm not sure. But anyway, they're calling for help, and we need to go save them. So what would be the quickest way to get to this person? I want you to think about that just for a second. Some of you might say, well, let's take the hypotenuse. Let's go the shortest distance possible. That's pretty valid, right? However, I know that I am not a faster swimmer than I can run. I know I am much faster on land than I am swimming, and I assume most of you are too. Right? It's going to take way longer to swim out there with all the waves and everything. So, yeah, I'm going to stay as long as I want on land, right? I'm going to come over here, and then I'm going to go up and save him. But the issue with path A is I'm just taking way too long. I'm running way over here. I'm not even running in the same direction that he is. So really the shortest way to go save him is to take path B, because I'm going to head in the same direction as where I want to go, but I'm going to spend more time on land and less time on water, and I'm going to get there quicker. And light does the exact same thing. Light takes the least path of resistance. Now what does that mean? What does it mean for light to travel as quickly as possible like the scenario? Well, it can be explained by the concept of refractive index. So the speed of light, when it's in air, travels at 671 million miles per hour. Now, we can't even think, we don't even have a gauge of how fast that is. But when light enters a material or a medium that's not air, it's going to slow down. Air or a vacuum is the fastest medium in which light can travel, in which it travels at that speed. And so this is like the water right here in this lifeguard scenario. So say this is a piece of glass that we're going through, or it's a pool of water, something that's not air. It's more dense, it has more material, there's more molecules to bump into. Light will take the shortest way to get across from it. So it's going to change its angle when it comes in here, and then exit back out in the same direction it's going, because light wants to get from here to over here. And so it's going to keep that same trajectory, but it's going to change the angle right there. So now these two angles are different. And the refractive index of the material describes how slow it is. Air would be the fastest. It has the smallest index of refraction of 1. And then other materials have varying refractive indices that are greater than 1. So these can be related to the concept called Snell's law, where if we take the ratio, the two refractive indices, and the sine of the two angles, these are equivalent. So say if we don't have this angle, we don't know what angle light's going to be refracted at, but we know what material we're going into and what angle we're shining it in on. Well, now we know how it's going to exit. So that's why Snell's law can be really useful. Now, how does this apply to the internet that we're talking about? Well, so there's this concept that now completes the whole word, total internal reflection. There exists a certain angle, according to Snell's law, that 100% of the light is totally internally reflected. And I've included this diagram here where we say we have air and a higher refractive index, and I'm putting my laser in here. Say if I have it in like the bottom of a pool or something like that, and I shoot the light straight up, it's going to go right through the material, and I change the angle a little bit, and some of the light's going to go through, it's going to refract according to Snell's law, and some of it's going to reflect. Change the angle again, some's going to reflect at the same angle that I pointed at, right? 30 degrees, point it, reflects at 30 degrees, but some of it comes through, and that angle is calculated with Snell's law. But eventually I'll reach an angle, which differs depending on what material I'm in, where all of the light is totally internally reflected. And you can calculate that angle just with this equation, using Snell's law that I showed on the other screen. So Snell's law right there, and that's the condition for the critical angle, in which light is totally internally reflected. So an example of this is used in fiber optics, and this is actually how internet works. That principle right there. We can already understand how it works. With the internet, there are optical fibers that run throughout the entire nation, connecting cities throughout the entire world. And these little fibers are about the thickness of a human hair. And I have a few examples I'm going to show you on these fibers in a second. But first, I just want to take a look at this picture and kind of show you this is the exact same concept that we were talking about, right? We have a higher refractive index than this outside, which is what we call the cladding, which is kind of the surrounding of here, of the air. It's higher than the air around here. And then we have a cladding that also loops around there to protect it from the outside. Because these fibers are so small, it needs some protection from the outside, right? And so we make sure to make this smaller than the inside, because that is exactly what we showed right here, right? We want the higher index of refraction on the inside. And so that's what's happening right here between N2 and N4. So when light goes in and we send it in at a certain angle, we can totally internally reflect it so that none of the light gets lost. So if I have a fiber stretching from Tucson to New York, I can put light in and I can get 100% of it out. And so you can send information, in pulses. When the internet communicates, send pulses of light. And you can think of this like waving my hand back and forth over this laser, right? Now I'm pulsing it. It's like turning it on and off. And that sends information in ones and zeros that can then be read by a computer and use information. Say when you text, right? When you are texting someone, you are sending over a certain type of light. It's a wavelength of, I think 0.155 microns. You are sending that type of light out of there in pulses through an optical fiber using TIR. And so now we can see that Snell's law connects the entire world. Some examples of this. I talked a little bit about our phones, how you text everybody. When you text out the entire day, right? When you're texting right now listening to this, you're sending these pulses of light through optical fibers to someone else. But teleprompters are also another example of using TR. It doesn't just have to be fibers. There's other applications to this in the world, which is what I just want to briefly touch on right here. So this teleprompter right here, if you've ever wondered how someone memorizes a whole speech, how does Obama go up there and say an entire speech off the top of his head? Well, he doesn't, right? He has a teleprompter. But that teleprompter works by having the message down there projected up onto here at a certain angle to where only he can see it, because all the light is totally reflected towards his eyes. And the rest of us out here, can't see the words on that screen. Netflix. Not just texting, but just any media is used for total internal reflection. And also probably one of the most important ways, once you start talking to someone, you start dating, right? Say you want to wife someone up, it's not going to work without total internal reflection. Diamonds do not sparkle without this concept. So if you're trying to buy a ring, just remember, it is optics that makes you have a happy life. Fingerprint scanners are another use of total internal reflection. Inside that device, connecting the entire world, as I said, so that you can watch your sport games with your friends so that you can have a good time. That's all optics at work. I have a couple examples right here. So this is a very blown up optical fiber. Much, much, much bigger than they actually are. An optical fiber is really the size of the hair, which luckily I found it because it's so small. So this would be an example of, say, an optical fiber. So as we talked about, if I send light in at this angle, it's going to come out of the other side. But as I change that angle, I will approach a critical angle to where all of the light, it's kind of hard because I'm doing this handheld, and keep in mind, you can only see it on the outside here because this is not an ideal optical fiber, right? It's a piece of acrylic. But the concept is being illustrated that if I shine it in, we can encapsulate all of the light inside of here to where all of it stays in and all of it goes out. Now the only reason that some of it's getting out is because this is just a non-ideal piece of acrylic. But I think this is going to be better illustrated with something that's a little more representative of how it actually works. So a little smaller piece right here. If I take the laser and I shine it in here, the right angle, all of it is exiting out of this side. Despite the little variations that you see in here from the non-idealities, the light will stay inside the fiber even though it's coiled up, and it will come out this side right here, which is a little hard for me to hold right now, but I hope you all can see that. All right, and even smaller than that, say would be all these fibers that I've clumped together right here. Same thing that will apply. Might be able to see a little bit of it coming out of the end. So that is TIR, where I'm shining this laser in and all of the light is totally internally reflected until it exits out the other side. I hope that was educational for all of you, that you learned a little bit about how the internet works, very simply. Thank you all for listening.